what should I say? I mean, like, so basically we are gonna go deeply into this 1D example, and we can say that we essentially understand everything, understand almost everything. I mean, quite well. Well, everything. And you know, in 1D, this is one of the reason why people typically say that this is sort of like it's integrable in 1D, meaning that it's typically solvable. And again, solvability for mathematicians is quite vague in certain ways, right? You know, so we have to make clear what it means. So anyway, so that's the goal. And this is a very so the example we are discussing is quite an you know, quite a favorite example in Hamiltonian dynamics and also for dynamical system people, because this is sort of very beautiful. And you can see, I mean, we have already talked about that, and then so let me recall it very quickly. Again, I'm respecting Fatih here, so we are considering the reversible Lagrangian, and a typical form is this Lagrangian, and we are going to focus on this Lagrangian in our for today. We're going to consider exactly the classical mechanics Hamiltonian and Lagrangian that we have h of xp equals to 1/2 the momentum square plus v of x, so total energy, right? You're going to see also clearly today where it comes into play. And Lagrangian, corresponding Lagrangian is going to be the difference of the kinetic energy and potential energy, right? This is a difference. Okay. And as we discussed for this kind of example, you know, they are part of, you know, a general class of reversible Lagrangian, or I mean, we even don't need the reversibility. The key thing we are using here is that we have Lxv is always greater than equals to Lx0, right? And therefore we have been able to characterize that minus C naught, our ergodic constant, whatever, is the minimum in x of Lx0, and it's also minimum in xv of Lxv. So that's the first claim we got. And the second claim we got is also that we have a complete characterization of the matter set in this case, or matter measures. So the matter set is going to be all the points x0 for which I have uh, uh, you know, X is in the arc mean, whatever, in a fancy way of L0. I mean, it's just the fact that, you know, you can either write this way or you can also write, you know, the other way. That way it achieves its minimum. Okay, so far so good. No, absolutely nothing sort of complicated here. So today I want to go further. So for the goal for today is the sort of like you know, understand Wickham solutions U minus, right? And then also not just that, but understand the deep dynamics behind that, you know. So in my lecture notes, I only wrote down the part about the solution and I left the part about the dynamics hidden so that we can discuss it more tonight. So, you know, like understand the Wickham solutions U and also understands about, you know, calibrated curves, or also like backward characteristic. You know, they are the same objects. Yeah. So that's our goal. And again, Please do stop me, discuss with me, or whatever. Bring up things, and you can see that actually my interpretation, my viewpoint is a tiny bit different with Hamiltonian dynamics. If some of you have taken courses in elementary or advanced Hamiltonian dynamics, you can see this example a lot. So I'm going in a bit different flow. Eventually we converge to the same thing, but I'm starting with PDE. Okay. um, um, okay, so let's start first with the PDE, and then we go from the PDE to discuss about the dynamics. So first start with finding U minus. And again, many times I'm gonna just make it to be U, so that I mean I'm I don't like the fact that I have to write down minuses so many times, but anyway, okay. Um, the first thing, for simplicity, we assume that V only has one maximum point. Okay, so that's for our convenience. We're gonna revisit the case where we have a lot of the maximum points later by the end of the lecture. So I mean because we can shift things around, it doesn't matter. It's a periodic environment, so when you shift things around, you can assume that the maximum of V is achieved at only 1.0, and because it's periodic, so it's 0 1, right? You just keep shifting the picture. um, so you see the graph of V is something like sort of starting with the maximum point, dipping down, going up again. I mean, it's one periodic, so if you draw the picture repeatedly in 0 1 2 3 4, you can also sort of like make it like that, going back and forth, going back and forth, going back and forth. Okay, so this is what I meant when I said that you can either consider the problem in the torus, or consider the problem in the whole R with one periodic function. So this is going to be our C naught, right? Because as you see, the definition is that C naught is the minus C naught is the mean of Lx0. So that means that, translated into this example, you would have minus C naught is mean of minus of V, right? So that meant that C naught is max of V, right? So we have been able to find that's our C naught, that's max of V at those points. Huh? And again, so let me write down. So we have C naught is equals to max of V, and it's equals to V0 or V1, doesn't matter. Okay, and we have the matter set, right? Just gonna be 1 point, right? Because in this case, again, I assume that we only achieve max at 1 point. Again, 0 and 1 are identical in the torus, right? Because you can, they're the same, represent the same elements. So that meant that the matter set is gonna be 1.00, right? So this is good. I'll mention. I mean, in this example, it's very simple, but but again, let's try to construct U minus first. So construct U minus first, right? Again, hiddenly we know that it's solving. So you know that U minus solves the stationary or the uh, so stationary or static problem without harm, right? It's all I said that in the context of uh, homogenizations or others, we say that it's a cell problem. So you can write out the problem rather clearly. So 1/2, again, I'm gonna omit the minus signs now. So it's inconsistent between the left and the right panel, but because u and u minus are identical, I'm fine. So I have this just very simple equation that I need to solve, right? So this is equal to C naught. Again, C naught is this max of V or V0, doesn't matter, okay? Yeah, so I mean, this is just a quadratic equation in u prime, right? So you just write out u prime of x squared equals 2 times C naught minus V of x. So, this is rather convenient, right? So it's exactly greater equals to 0. So everything is admissible, right? And you can see clearly from this threshold that C naught cannot get smaller, because if C naught were to be smaller, then I wouldn't have this right hand side here greater than equals to 0, right? Um, and I need things to be greater equals to 0 so that it's admissible. Fine, right? So therefore, from here I would get that u prime of x is equals to either plus or minus the square root of 2 times c0 minus v of x. Okay. Yeah. So that's good. Again, I mean, however, I mean, we have to be careful here because we are doing sort of like selecting either it's the plus of the square root or minus of the square root, and it's not clear at all. What should we do, right? But looking back, we remind ourselves that u is periodic, right? Which which means that I should have u0 equals to u1. Okay, so in order to I mean have this kind of compatibility condition, right? Then I should have, this is by the fundamental theorem of calculus, tells me that integral from 0 to 1 u prime of x dx must equals to u1 minus u0, which is 0. So that's a compatibility condition, right? So let me highlight, we have two things. We have u prime equals to root plus or minus root of that, and however, I need to also uh, keep in my mind that like the integral of u prime is 0, right? So therefore, I mean, I have to balance things out, right? I mean, I can, again, this is very suspicious up to this moment, right? Because there can be different ways to different ways that you can choose things, but I mean, what it meant is that you need to choose u prime to be positive in certain parts and negative in certain parts, and then the summation of the positive and the negative part cancel out, right? Again, it just that, but it doesn't guarantee us at all like how many choices can we have over there. Like, actually you can have many such choices. So I'm gonna make one choice and you can be very suspicious of me, like, why did I make that choice? But I claim that this is a correct one again. Why is it? We're gonna prove it, but I mean, okay. Any question for me up to this point? Okay. No. All right. So now, let me move forward and telling you now. Like, how do we do this, right? So again, this is by no means an obvious choice, but I mean, like, for some reason I decided to go, like, so graphically this is 0, this is 1. I decided to go, from 0 go all the way to certain points z, and here I decided to choose that u prime of x is always greater than equals to 0. Okay, so in the first part of the interval, I chose u prime to be always greater or equal to 0, and that meant that here we are choosing it such that u prime of x equals to root of 2 c naught minus v of x for 0 less than equals to x, less than x. Less than equals is like, that's actually fine. Okay, doesn't matter. Less than z. Okay, so in some part of the interval, I chose u prime to be always non-negative. So I'm going up, right? U is increasing. Okay, and then up to some point, I have to stop and switch to the negative branch so that they balance things out, right? So in other words, for the other one, I'm balancing it out. So I'm choosing in this branch that u prime of x is less than or equal to 0. So, you know, going from here to here is being negative, and that would meant that I would select u prime of x is minus root of 2 c naught minus v of x here for z less than x less than or equals to 1. Okay, and here, you know, let's look at the into the left panel. You know, we choose z, there's a unique z so that it balances out, right? So there's a unique z so that the integral from 0 to z of this continuous function equals to the integral from z to 1 of this same continuous function. So I choose a splitting point in which the weight of the function is balanced between 0 to z and z to 1, and we splitted it. You know, so the graphical picture of that is like, you know, you have the function root of 2 times c naught minus v, right? And this function obtains its minimum at 0 and 1. So this function is equal to 0 and at 0 and 1. And because the function only has one minimum at 0 and 1, so it's increasing and then decreasing. It's sort of whatever. It's sort of a graphical picture. And then we choose z to be that splitting point. Again, you can question me right away here, right? You can say, why did I make this choice? You know, equivalently, you can make the same choice by, you know, choosing from 0 to z to be negative and then z to 1 to be positive. That could be still the same, right? But what I claim is that this is the only choice that's gonna make sense. So it's I have to choose again. I haven't proved anything, but I had to choose in this way so that it's gonna be a Wickham solution. Okay. So again, stop me or ask me question if you have some concerns. All right, so if there is no further question, then let me move on and then tell you again a little bit about this U, and then I claim that it's a Wickham solution. Okay? And for those of you again who have learned about viscosity solution, U or U minus here is exactly the viscosity solution of the stationary or static equation. Okay? But again, it doesn't matter if you haven't learned it because we are just doing it now. And then, okay, so if I chose it that way, then I can just define U now, right? For the time from 0 to z, I'm just integrating the derivative, right? And then for z from x from z to 1, I'm just integrating from x to 1 of this function. So clearly you see that when x equal to z, the two integrals are equal, and then at x equal to 0, 1, the either the upper or the lower integral equals 0. So it is totally valid and nice. And the geometric picture of u minus is beautiful. Not quite, but it's like this, right? You start from 0, and then you increase up to certain value here, and then you decrease again, right? So yeah, let me redraw this picture here. 0 and 1. maybe Z. Yeah. So we are increasing from here after some point, and then decreasing down. Okay. So maybe let me write that in this left branch again. I have u prime equals to root of 2 c naught minus v of x. Okay, that's this branch. And then in the other branch, I would have u prime x equals to minus 2 uh, c naught minus v of x. Okay, so clearly that you see that at the maximum value of u, which is the point I'm highlighting here, is not differentiable, right? You have that, so at this point it's not differentiable, right? Because you can write down, right? I can write down like u prime of z minus is equals to root of 2 c naught minus v of z. You can remember that v of z is less than c naught, so this is a positive value, right? So it's greater than 0, greater than minus root 2 c naught minus v of z, which is u prime of z plus, right? So clearly that the function is not differentiable at that point. And I claim, so we claim that this u is a weak KM solution. Again, in the PD language, we say that u is a viscosity solution. Okay, so that's our claim. And this is remarkable, but also troublesome. It's troublesome because it tells that you know, the Wickham solution or the viscosity solution is not differentiable everywhere, right? It's not C1, of course not C2 or so. So clearly the framework in which we would hope for something C2 or C1 earlier, as I told you, or I mean, like also like in the classical uh, approach in Hamiltonian dynamics was to find some smooth or C2 functions to do change of variables. Uh, it's a canonical transformations. It just doesn't work, right? Because this function is merely Lipschitz. I mean, it's fine in the two branches, but it's not differential at one point. So that's really problematic. So that's the first thing. Again, I will prove this claim and discuss that with you. Uh, but before that, so this is to be proved soon. But before that, there's one more clear thing is that what I wrote down here in the lemma by the end of the pre-lecture notes, that not only we have u is a Wickham solution, but in this case, all of the Wickham solution got to be u plus c, right? Why so? Because remember that the projected matter set is only one point. So therefore, you know, so not only that, but also that all Wickham solution are, in this case, u plus c, for c being just a shifted constant. So why? You know, again, because you have, let's say, let's take let's say w to be another Wickham solution, right? Again, you just take any other Wickham solution. So recall that M0, the projected matter set. This is the projected matter set. which is also our uniqueness set, right? So I proved to you a very important result that uniqueness set. I'm sorry. That this projected matter set is the uniqueness set, right? So if you take W to be any Wickham solution, you can compare W with U at the point 0, right? So you can just take that Wx plus what plus U0 minus W0. So you just add a constant, right? So it's still a Wickham solution, right? So nothing there, and you can call this one W tutor of X if you want. Again, I'm writing the proof a little bit different with what I wrote, but it's the same. Then you have W tutor of 0 is equals to U0, right? Uh, so W tutor and U are both Wickham solutions, and they agree on the projected matter set. So this implies that W tutor has to be U. Okay, so in other words, I would have that, again, Wx is just Ux plus a constant C, right? So we are done. Yeah, so what is really, really remarkable and beautiful is that when you have the projected matter set is only 1 point, then you have that all Wickham solution got to be described in this family, right? Essentially, you have uniqueness here. I mean, up to additive constant. Any question for me here or any point you want to discuss before I move on to the last part, which is actually, um, you know, actually the most important part. Yeah, go
Yeah.
ahead.
So I guess so in that last step there, we know that W tilde 0 agrees with U 0. So why does that allow us to conclude that their two functions are the same?
Oh yes, because we proved earlier a result. So there was an earlier result. I forgot in which lecture the result. Uh, yeah, it's actually good to record here that we have uniqueness with respect to the matter projected matter set. So the earlier result we proved was that if U and V are two Wickham solution. Sorry, my writing. Oops. Two Wickham solution, and if you have that U equals to V on the projected matter set, then you would imply that U is equals to V on the torus. So that was the earlier result by using the fact that the projected matter set is a uniqueness set. You know, so we are using that earlier result. I think we proved it maybe 2 lectures ago or something. It's a very deep result, right? But I'm using it now here because I'm using that in our very, very baby example, the projected matter set is only 1 point, right? So therefore, you see that for the W, I shifted it by a constant to have W tilde, and W tilde equals to U at 0. So that must meant that they are the same.
I see. Thank you.
Yep. So thanks a lot for the question. So you see, I mean, this is again, as I said, one of the very few classes that I have ever taught that is focusing on exactly one single topic. So you see that I'm using everything I have developed from lecture 1 up to lecture 30, right? So you see every lecture is quite simple, but because it's really twisted in the sense that I'm using everything. So, it's different with other like PD classes or topic courses in which, I would teach, uh, one topic in few weeks and then move on to the other topic. So sometimes they can be disconnected, but here it's just really like going in the same thread from the beginning to the end. um, yep, so great. So it's a beautiful result, right? So we have that if the projected matter set is only 1 point, then we would have that we only have to shift it. Maybe the picture is this. The picture is this is the function u. This is 0. Right? U0 surely equals to u1. And then you have another functions w. I don't know what w is, but maybe it's like this, right? So I'm shifting it down. I'm just shifting it down by making its copy and shifting it down. What? Okay, I'm shifting it down to another function w tutor here, so that I have w tutor of 0 equals to u of 0, right? And then because of the uniqueness result, I must have that then w tutor must equals to u, and that's sort of like the idea. Okay, right. So thanks for the question. Any other concern before I move on to? Let's see. I wanted to copy something down so that I don't have to repeat.
So one question. So the z you choose here is exactly where v has a minimum?
No. 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 I'm choosing z so that it's balancing out the two integral.
Okay. Yes. I
Right.
see.
Yeah. Again, maybe my drawing skill was not good, so it's seemingly that I was making it that way, but no. Okay. Yeah, I mean z is somewhere so that it's divided between the two. Yeah. Again, maybe I'm not gonna copy that picture because of what you just said. Okay, maybe let me just copy this part so that yeah, maybe just this part is fine. And then paste. Yeah, let me go down and discuss the final part with you. Okay, so by the way, thanks to Sun, he told me like the other day that there was a glitch with Zoom or whatever iPad, because whenever I'm teaching, I'm seeing on my screen for the it's always 9:41 Tuesday, January 9th, and then it was always confused, but seemingly it's sort of a glitch for Apple or something, from Apple or something. Okay, so maybe let me redraw the picture here so that I'm not confusing you guys about our choice of z. So we have this function going from 0, right, going up, down, something like that. I'm still not good. Yeah. Sorry. My drawing skill is not super. Okay, maybe this is better. Okay, so this is 1, this is 0, and we pick a point z so that just the weight between the two parts of the same. So maybe you can say that this is the graph of the function root of 2 c naught minus v of x. Okay, and again, you choose it so that the weight in this part is the same like in the other part, right? I don't want to lose time highlighting this, but okay, fine. Okay. Right. So so what I want to show you is that, so I mean, clearly we have we have, like 1/2 u prime of x square plus v of x equal to c naught almost everywhere, right? In fact, it's everywhere except at the point z, right? So that's fine. So what I'm owing you is the fact that we, like by the definition Wickham solution, right? This is okay already almost everywhere, and it's equivalent to saying that u is dominated by L plus C naught. So that's fine, right? So what we need to show, there's one missing thing, one missing point, is that what I owe you is that we need to show that for every point, say x naught in the torus, in this case I identify it to be just the interval 0, 1, we can find a calibrated curve gamma mapping from -infinity 0 to just the torus such that gamma 0 is equals to x naught, right? That's exactly what I'm owing you, right? And how do we prove this thing, right? And this is exactly the point in dynamics, and this is actually one of the, as I said, one of the favorite example that people have been actually doing there, and always that it occurs in all the courses in classical mechanics or something like that, at least from my understanding. How do I do this? Okay, now you see, as I told you, I'm doing it in a very different and reverse way, because I introduced you to use the PDE, and I'm trying to solve you. I have the formula for you here, and now I'm doing it reversely, right? I'm gonna use it to construct the calibrated curve. Okay, maybe maybe it's a good idea to also draw this picture here. This is 0, this is 1, this is a point z, not the middle point, but maybe these here, and also that I have 0, z, 1, and the solution u gonna look like increasing to this point and decreasing to here. Okay, so this is u. Okay, now I'm gonna use it to construct calibrated curves, and you see that it's really fun, and it how do we do this? So we're gonna use exactly the earlier use the, either you can use the Euler-Lagrange equation or the Hamiltonian system. Okay, so I mean, I would like my curve to have gamma 0 equals to x naught, right? And again, I would have to be careful if x naught equals to z, but let's just write it down. And I would need to have my gamma prime of s. Remember when I write out the calibrated curves, right? Gamma prime of s is x prime of s, which is nothing but dph of xs ps. Okay, and again the Hamiltonian, again I have x h of xp equals to 1/2 p square plus v of x, right? So dp is just p, right? So it's exactly ps. And remember what's ps? Ps is u prime of xs, or u prime of gamma s. Okay, so by using exactly the Euler-Lagrange or the Hamiltonian system, I can write down the equations for my calibrated curve. And I have the exact formula for my calibrated curve. So that's really, really beautiful. Okay. Now, again, I'm keeping the picture here. You see that there are cases, right? If x naught is sitting on this side, or x naught is sitting on the other side, or stuff like that. But let's just write it down. Okay. So case number 1, if 0 is less than or equals to x naught, less than z, it can be equal. I'm going to make it equal right away. Okay, you just write out your calibrated curve. You have gamma 0 equals to x naught And for s less than 0, gamma prime of s equals to u prime of gamma s, which is equals to, I have the formula, right? So u prime is positive here, okay? You see? So it's exactly root of 2 c naught 0 minus v of gamma s for s less than 0. Okay, so you see that the whole thing fits together. It's really beautiful. And in fact, you see that I can also make it equals to z. Doesn't matter because before it's less than z. So if this is 0, this is z, this is my point x naught, then you have your calibrated curve is sort of moving from here all the way up to x naught. It's gonna be gamma s here. Okay, and what is remarkable is two things. Is that if x naught equal to 0, then your calibrated curve is nothing but a stationary point, which is just 0 for OS, right? So it just sit there exactly at that point. And if your point x naught is greater than 0, then it's this point, and then your calibrated curve is going, increasing to x naught, and up to that point, right? And similarly for, again, there's one hidden point here I haven't told you, but let me tell you case 2. Similarly, if z is less than equals to x naught less than equals to 1, then your calibrated curves could be decreasing. Okay, so I'm trying to do it quick so I can tell you one really important hidden point. This is x naught, then your calibrated curve gonna decrease from somewhere to the point x naught. Okay, and in particular, at x equal to z, you have two calibrated curves ending at z, right? Because at the point z you have two calibrated curves. If x naught equals to z, then one calibrated curve starting from somewhere and just keep running to this point. This is gamma 1 of s, and you have the other calibrated curves also coming from here and running to x0 equals to z. So those two running, and because the fact that you have two calibrated curves and they run into each other, it makes the u not differentiable. Actually, it's exactly like, not exactly, but it's precisely the crossing of characteristics. If you have learned about characteristic method in chapter 3 of Advanced. Okay, any question for me up to this point before I move on to the last magic piece? Any question? Concerns? Okay, so here's the last magic piece. That you have seen that 0 is the sort of you can say that in the language of dynamics is a stable attractor or whatever, right? I mean, if you stay at 0, you are always equal to 0. I mean, it's a stationary point, but it's also stable. Now, there's one hidden point I haven't told you about the gamma here, right? I haven't told you at all about this situation, right? That what's going to be the behavior of gamma. I said gamma is starting from somewhere and increasing up to x naught, right? So, like, does gamma starting from 0 and then going to x naught, or does it just start from somewhere greater than 0 and going to x naught, right? So that's the question. Okay, so let's focus on the last point. So the last magic point. So I have, let's say, 0 less than x naught less than equal to z. So 0 x naught here, z 1, and I have gamma prime of s equals to root of 2 c naught minus v of gamma s for s less than 0, right? So then the question is exactly the normal question that we would ask in dynamic, or like, is the behavior as s goes to minus infinity of gamma s is what, right? Does it exactly going to 0? You start at this point and you're going backward, right? Are you really going, I'm switching the time now, right? I'm going backward in time, so gamma s. Are we gonna approach the point 0 in a finite time or infinite time? Okay, that's the question. So here's a fun point. So the claim that if p is c2, then gamma s is always greater than 0 for os, greater than minus infinity, and limit as s goes to minus infinity gamma s is 0. So 0 is a stable attractor, right? Your calibrated curve is going to 0, slowly approaching 0, but whatever, but it's never gonna reach 0 in a finite time if v is c2. Okay, so let me give you a proof of this, and then I'm gonna give you the case that if v is less regular, then in fact it can reach 0 in a finite time. So I don't know, it's beautiful, right? Assume that I would have gamma minus t is equal to 0 for some t, right? So I'm just going, reaching 0 in a finite amount of time, right? So let's write down. I have that meant that the integral from minus t to 0. This is typically the calculation that people have done in Hamiltonian dynamics. I forgot the name. I mean, I'm doing it like in PDB points. I'm taking this integral, phase space, whatever integral. Okay. So this integral must be 1, right? I mean, the thing inside is 1. So it's t, right? So that meant that you can say that the time it takes for the orbit to go from 0 to x0 to 0 is t. Okay, so that's the integral. And up here you can do change of variable, right? Integral from minus t to 0 d of gamma s over root of 2 c naught minus v of gamma s. What? Right? And you do change of variable. You do d gamma s over there, right? So you switch to dx over root of 2 c naught minus v of x. When x is minus, when gamma 0 is x naught, gamma, gamma minus t is 0. So you have the integral from, you have the integral from 0 to x0 dx over root of that equals to t, right? But remember that your function is c2. So, this one behaves what? This one behaves like at v0 is the maximum point, right? Max of v. So, so near 0, this one would behave like the whole thing would behave like 1 over x, right? Because because you write out the Taylor transform, Taylor expansion, right? Vx equal to v0 plus v prime of 0x. This is equals to 0 plus v double prime of something x square over 2, right? And clearly that near 0, this one would behave like 1 over x, which means that this integral diverges. Okay, so that gives us that this is a contradiction. Yeah, so you see that that if our function, and in general in classical mechanics, our potential energy, everything is ck, right? So in this case, if everything is ck, then we couldn't reach zero in a finite amount of time. Okay, so that I'm done. So let me just conclude. I'm overboard a bit today, but if let's say that Vx minus V0 is sort of like less than equal to c times x to the power theta for theta less than 2. So you see that if our function is less regular, so it is sort of like less than c2, c1 alpha or something like that, then the integral, then the above integral converges, right? You know, this integral I'm highlighting now is fine. Okay. So if the integral converges and I can find a time t, then how does my calibrated curve behave? And then I'm done. So if that is the case, and you have this is x naught, this is 0, you go from here. So this is gamma s. You go up to gamma minus t, you reach the point 0. Then your calibrated curve is going to be gamma s is going to be 0 if s is less than equal to minus t, and then just gamma s for minus t is less than s less than 0. So that meant that you go from x naught, you reach 0 in a finite amount of time, and then you stay there indefinitely. You get to an equilibrium point and you stay forever. So you see that regularity now comes into play, and a lot of beautiful things are, you know, appearing. But so far, people can only do this thing for one day. So it's a case in which you have integrability. Everything is solvable. Okay. Any question for me? A quick question is fine. Otherwise, I have to. Okay. All right. So thanks a lot. And again, welcome back. We have 4 more weeks to go, including today. And okay. let's try to enjoy the last 4 weeks and do beautiful stuffs, and then we have time for research and other stuffs after the semester ends, right? Okay. So thank you all. I will try to have the next lecture notes posted in a timely manner. Okay. Bye for now. Okay.